So if you've got a belief, but the belief is shrouded in uncertainty, then you can improve the accuracy and the confidence in the belief by acquiring new data. But the data may be costly to acquire in time and money, and so you want to choose carefully what your next data point will be. And that's what the machine does for us. Once we can get the slides working, I want to show you how we apply that to a single quantum dot device in the laboratory. This is a device which is parameterized by the bias voltage and by the gate voltage, and we measure the current through it. And the machine is trained in advance on a combination of simulated and experimental data. And then what it does is, on the basis of, it makes some very few measurements. On the basis of those sparse measurements, it makes some projections. And the projections, because of the uncertainty, differ. And on the basis of those differences, the machine decides where the next measurement should be. It calculates an acquisition map, and the acquisition map is most strongly colored where the data will bring the most benefit in updating the belief. The machine makes the measurements at the maxima of the acquisition map, then it makes some new projections, calculates a new acquisition map, and iterates round, increasing the accuracy and confidence of the belief as time goes by. So that's shown in the right-hand panel there, and as soon as we can get rid of that, diagram here is the measurements that have been made so far. You can see they're very sparse, 8 by 8. Here's the acquisition map. It's dark where the data have already been measured. Where it's most strongly colored, that's where the next measurements are going to be. And if we can run this now, you'll see it actually doing that in real time, calculating the map, making the measurements, updating the map, making some more measurements. And it goes pretty fast if you show it now, David, but what you'll see is that very quickly you get almost as much information as you're going to get when it's finished measuring the whole thing. So by now, you've already got a pretty good idea of the shape of these Coulomb diamonds and the parameters, and now it's finishing off the whole job. Now, that's making measurements. As quantum computing gets scaled up, but this applies to other technologies too, tuning the devices is going to become increasingly challenging and is going to require automation. The results I'm going to show you, the method is applicable to any number of different implementations. The one I'm going to show you is to devices that embody singlet triplet qubits, for which you need 2 quantum dots at a temperature that's colder than anywhere we know of in the universe outside a human laboratory. Here's the double dot device, and the key thing is this has got 8 different electrodes. Each of them has such and such a range, say plus or minus 2 volts, and only about 1,000th of that range is going to be right for the device actually to work as a qubit. But this is 8-dimensional space, so it's 1,000th times 1,000th times 1,000th. So the needle is 1 over 10 to the 24, if you like, of the size of the haystack that you're looking in. And the method we're using here is deep reinforcement learning. It makes an initial measurement. Remember, this is really in 8 dimensions. I'm just showing it in 2. And the machine then, on the basis of its previous training, decides which of the 4 adjacent squares it should next measure in. And so it carries on making the measurements until down here it will finally find some triangles, bias triangles, that correspond to being suitable conditions for operating as a qubit. This is going to be essential for technological applications. It's now so efficient and so much faster than a human doing it that students in the lab don't want to tune these devices up by hand anymore. They just want to use the machine for it. But these methods may also be applicable to science, because Bayesian probability is all about confidence in beliefs in the face of uncertainty. If the next data point lies outside the predicted range of uncertainty, the machine can recognize that as a surprise. And the ability to recognize a surprise, I think, is a crucial component of science discovery.
Thank you very much.